नमस्कार, मैं आनंद कुमार खत्री। आज के हमारे लेक्चर का विषय है क्लाइमेट पार्ट 4, एटमॉस्फेरिक प्रेशर एंड विंड। Atmospheric pressure and winds are both significant controlling factors of Earth's weather and climate. Although these two physical variables may at first glance appear to be quite different, and they are in fact closely related. Wind exists because of horizontal and vertical differences. In pressure yielding or a correspondence that often makes it possible to use the pressure distribution as an alternative representation of atmospheric motion. Pressure is the force exerted on a unit area, and atmospheric pressure is equivalent to the weight of air above a given area on Earth's surface or within its atmosphere. This pressure is usually expressed in millibars or in kilopascals. Distribution of pressure on a map are depicted by a series of curved lines called isobar, each of which connects points of equal pressure. At sea level, the mean pressure is about 1000 MB, varying by less than 5% from this value at any given location or time. Mean sea level pressure values for the mid-winter months in the northern hemisphere are summarized in this first diagram, and mean sea level pressure values of the mid-summer months are illustrated in the next diagram. Since charts of atmospheric pressure often represents average values over several days, pressures features that are relatively consistent day after day emerge, while more transient, short-lived features are removed. Those that remain are known as semi-permanent pressure centers and are the source region for major relatively uniform bodies of air known as air masses. Warm, most maritime tropical air forms over tropical and subtropical ocean water in association with the high pressure region prominent here. Cool, moist maritime polar just south and east of the air, on the other hand, forms over the colder subpolar ocean waters just south and east of the large winter oceanic low pressure region. Over the continent, cold dry continental polar CP air and extremely cold dry continental Arctic CAR air forms in the high pressure regions that are especially pronounced in winter, while hot dry continental tropical air forms over hot desert like continental domains in summer in association with low pressure areas, which are sometimes called heat lows. This is the diagrammatic presentations. A closer examination of the diagrams above reveals some interesting features. First, it is clear that sea level pressure is dominated by closed high and low pressure centers, which are largely caused by the differential surface heating between low and high latitude and between continental and oceanic regions. High pressure tends to be amplified over the colder surface feature. Second, because of seasonal changes in the surface heating, the pressure centers exhibit seasonal changes in their characteristics. For example, the Siberian high elevation low and Icelandic low that are so prominent in the winter virtually disappear in summer as the continental region warm relative to surrounding bodies of water. At that same time, the Pacific and Antarctic high amplifies and migrate northwards. At altitude well above Earth's surface, the monthly average pressure distributions show much less tendency to form in closed centers but rather appear as quasi concentric circles around the poles. This more symmetrically appearance reflects the dominant role of meridional differences in radiative heating and cooling. Excessive heating in tropical latitude, in contrast to polar area, produce high pressure at upper levels in the tropics as thunderstorms transfer air to higher level. Wind relationship of wind to pressure and governing forces. The changing and pattern with wind patterns are governed by Newton's second law of motion, which states what the sum of the forces acting on a body equal the product of the mass of that body and the acceleration caused by those forces. The basic relationship between atmospheric pressure and horizontal wind is revealed by disregarding friction and any changes in wind direction and speed to yield the mathematical relationship where u is the zonal wind speed, v the meridional wind speed, and omega the angular velocity of the earth rotation, phi the latitude, p the air density, and the p no rho the air density, p the pressure, x and y the distance towards the earth, and east and north respectively. This simple non-accelerating flow is known as geotropic balance and yield a motion field known as the geostrophic wind. Equation first expressed for both the x and y direction, a balance between the force created by horizontal differences in pressure. More specifically, the observer on the ground experiences the Coriolis forces as a deflection of the relative motion to the right in the northern hemisphere and to the left in the southern hemisphere of particular significance. In this simple model of wind pressure relationship is the isobar with the low pressure of the observer's left as the looks downwinds in the northern hemisphere and on the his right in the southern hemisphere. Wind speed increases as the distance between isobar decreases can be added to this model with relative ease in a flow representation known as the gradient wind. Cyclones and anticyclones. Cyclones and anticyclones are regions of relatively low and high pressure respectively. They occur over most of Earth's surface in a variety of sizes ranging from the very large semi-permanent examples described above to smaller, highly mobile systems. The latter are the focus of discussion in this section. Common to both cyclones and anticyclones are the characteristics circulation patterns. The geostrophic wind and gradient wind model dictate that in the northern hemisphere Flow around a cyclone, cyclonic circulation is counterclockwise, and flow around an anticyclone, anticyclonic circulation is clockwise. Circulation direction are the reversed in the southern hemisphere. The cyclones that form outside the equatorial belt, known as extropical cyclones, may be regarded as large eddies in the broad air current that flows in the general direction from west to east around the middle and higher latitudes of both hemispheres. They are essential part of the mechanism by which the excess heat receiving from the suns in Earth's equatorial belt is conveyed towards higher latitude. These higher latitudes radiate more heat to space than they receive from the sun, and heat must reach them by winds from the lower latitude if their temperature is to be continually cool rather than cold. Strong horizontal gradients of temperatures are particularly favorable for the formation and development of cyclone. The temperature difference between polar regions and the equator build up until it becomes sufficiently intense to generate new cyclones as their associated cold front sweep equatorward and their warm fronts more poleward, and new cyclones reduce the temperature differences. Thus, the wind circulation on Earth represents a balance between the heating effect of solar radiation occurring in the polar region and at the equator. Wind circulation, though, through the effect of cyclones, anticyclones, and with wind system also periodically destroy this temperature contrast. Cyclones of a somewhat different character occur closer to the equator, generally forming a latitude between 10 to 30 north and south over the ocean. They generally are known as tropical cyclones when their winds equal or exceed 74 miles per hour. They are also known as hurricanes if they occur in the Atlantic Ocean and the Caribbean Sea, as typhoons in the western Pacific Ocean and the China Sea, as the cyclone of the coast of Australia. These storms are of smaller diameter than the extratropical cyclones, ranging from 100 to 500 km in diameter, and accompanied by winds that sometimes reach extreme violence. These storms are more fully described in the article Tropical Cyclone. This is the top view and vertical cross sections of a tropical cyclone. Extratropical cyclones. Of the two types of large scale cyclones, extratropical cyclones are the most abundant and exert influence on the broadest scale. They affect the largest percentage of Earth's surface. Furthermost, this class of cyclone is the principal cause of day to day weather changes experienced in middle and high latitude, and thus is the focal point of much of modern weather forecasting. The seeds for many current ideas concerning extratropical cycles were sown between 1912 and 1930 by a group of Scandinavian meteorologists working in Bergen. For this reservoir to be tapped, a cyclone called a wave frontal cyclone must develop much in the way shown in the diagram. The features that is of primary importance prior to the cyclone development, cyclogenesis, is a front represented in the initial stage. Cyclone development is initiated as a disturbing along the front, which resorts to the front into the wave-like configuration. As the pressure within the disturbance continues to decrease, the disturbance assumes the appearance of a cyclone and forces poleward and equatorward movement of warm and cold air, respectively, which are represented by mobile frontal boundaries. This is the evolution of a wave frontal cyclone. Cold air blue and arrow cold air flow, warm air pinkish and arrow red warm air flow. This is the initial stage, wave appearance and cyclonic circulation. The life cycle of such an event is typical several days, during which the cyclone may travel from several hundred to a few thousand kilometers. In this path and wake occur dramatic weather changes, a typical sequence of weather possibly resulting from the approach and passage of a cyclone and its fronts through an area is depicted in the diagram. This is the cross sections of clouds and precipitations often found along the cross sectional line AB in the panel D. The passage of the cold front is marked by the influx of colder air, the formation of the stratocumulus clouds with some lingering rain or snow showers, and then eventual clearing. While this is an oft repeated scenario, it is important to recognize that many other weather sequences can also occur. The actual formation of any area of low pressure requires that mass in the column of air lying above Earth's surface be reduced. This loss of mass then reduces the surface pressure in. While extropical cyclones form an intensity in association with fronts, there are small scale cyclones that appears in the middle of a single air mass. A notable example in a class of cyclones generally smaller than the frontal variety that form in polar air streams in the wake of a frontal cyclone. These so-called polar low are most prominent in subpolar marine environment and are thought to be caused by the transfer of heat and moisture from the warmer water surface to the into the overlying polar air and by supporting middle tropospheric circulation features. Other small scale cyclones form on the lee side of mountain barriers as the generally westerly flow is distributed by the mountain. These lee cyclones may produce major windstorm and dust storms downstream of a mountain barrier. This is the satellite image of a large dust storm in the Taklamakan Desert, China. Anticyclone. While cyclones are typically a region of inclement weather, anticyclones are most usually meteorological quiet region. Generally larger than cyclones, anticyclones exhibits persistent downward motions and yield dry, stable air that may extend horizontally may many hundreds of kilometers. In the most cases, an actively overdeveloping anticyclones forms over a ground location in the region of old cold air behind a cyclone as it moves away. This anticyclone forms before the next cyclone advances into that area. Such an anticyclone is known as an cold anticyclone, a result of the downward air motion in the anticyclone however, is comparison of the descending air. As a consequence of this compression, the air is warmed. Thus, after a few days, the air comprising the anticyclone of at level 2 to 5 km above the ground tends to increase in temperature, and the anticyclone is transformed into a warm anticyclone. Warm anticyclone moves slowly, and cyclones are diverted around their periphery during their transformation from cold to warm status. Anticyclones usually move out to the main belt, followed by cyclone in the middle latitude, and often elongate with the quasi-permanent bands of relatively high pressure found in the both hemisphere ground latitude 20 degree to 30 degrees, the so-called subtropical anticyclone. The descent and warming of the air in an anticyclone might be expected to lead to the dissolution of clouds and the absence of rain. Near the center of the anticyclone, the winds are light and the air can become stagnant. Air pollution can build up as a result. The city of the Los Angeles, for example, often has poor air quality because it is frequently under a stationary anticyclone. Anticyclones are often regions of clear skies and sunny weather in summer. At other times of the year, cloudy and foggy weather, especially over wet ground, snow cover, and the ocean, may be more typical. Winter anticyclones produce colder than average temperature at the surface, particularly if the skies remain clear. Anticyclones are responsible for periods of little or no rain, and such periods may be prolonged in association with blocking highs. Cyclones and anticyclone climatology. Migrating cyclones and anticyclones tend to be distributed around certain preferred regions known as tracts that emanate from preferred cyclogenetic and anticyclogenetic regions. The contrast between the winter and summer mean sea level pressure diagrams also indicates the typical cyclone track for both January and July. Favored cyclogenetic regions in the northern hemisphere are found in the lee side of the mountain and of the east coast of continents. Anticyclones tends to migrate equatorward out of the cold air mass regions and then eastward before decaying or merging with a warm anticyclone. Like cyclone, warm anticyclones also slowly migrate poleward with the warm season. Local wind scale classes. Organized wind systems occur in spatial dimension ranging from tens to of the meters to thousands of kilometers and passes residence times that vary from seconds to weeks. The concept of scale considers the typical size and lifetime of a phenomena. Since the atmosphere exhibits such a large variety of both spatial and temporal scale, efforts have been made to group various phenomena into small classes. A second class is known as the synaptic scale. Local wind system. The so-called sea and land breeze circulation is a cool local wind system typically encountered along coastlines adjacent to the large bodies of water and is induced by differences that occurs between the heating or cooling of the water surface and the adjacent land surface. Water has a higher heat capacity than to the material in the land surface. Daytime solar radiation penetrates to several meters into the water. The water vertically mixes and the volume is slowly heated. This is the typical sea breeze. Afternoon and land breeze, night circulation with associated cloud formation. This is the when the valley floor forms during the day. Warm air rises up the slopes of surrounding mountain and hills to create a valley breeze. At night, dense, cool air slides down the slopes to settle in the valley, producing a mountain breeze. Zonal surface wind. The diagram of the January and July mean sea level pressure reveals that on the average, certain geographic location can expect to experience winds that emanate from one prevailing directions largely dictated by the presence of major semi-permanent pressure system. Such prevailing winds have long been known in marine environment because of their influence on the great sailing ship. This is the general patterns of atmospheric circulation over an idealized Earth with a uniform surface left side and the actual on the right side. Both horizontal and vertical patterns of atmospheric circulation are depicted in the diagram of the actual Earth. This is the position of jet stream in the atmosphere. Arrows indicates directions of mean motions in a meridional plane.